So to summarize where we're at, we've defined both the scalar line integral, so line integral of a scalar function along the curve C, and we've defined the vector integral, or the vector line integral along a path C as well. And one of the most important points about these line integrals is that in general they are path dependent. They depend on the path. So we'll kind of write this down. So the line integral of a scalar field we've suitably defined as, the notation for this is just the integral over C of the function phi with respect to arc length is the accumulation of the function phi on the curve C and the line integral of a vector field on a curve C was defined as the integral of f, the dot product of f, some vector along the curve integrated with respect to arc length. This is the accumulation of the vector field f in the direction of u hat along C. And for a very special case of this, we've seen that and when in most sources when they say line integral, this is what they mean, the line integral of a vector field. Tangent to C. So this is when u hat is chosen to be the unique tangent, or the tangent vector to the curve C. This is the integral of f dot this unit tangent vector, or just simply put f dot dr. And what we're going to do is we're going to kind of investigate this special line integral some more as we kind of move through the lecture. So all of these line integrals in general, important point. In general, line integrals depend on C. The way of writing this is that they are path dependent. But the following example is a very important example because it's going to show that this idea has very important exceptions. So sometimes, for certain types of vector fields, this tangent line integral is actually not going to be path dependent. It'll be what's called independent of path. So what we'll do is we'll consider a mass m moving in a gravitational field close to the surface of a large gravitational body. So for instance, you can think of projectile motion on the surface of the Earth. And for mass moving in this situation, we know that the force on the mass, if we orient ourselves with respect to the ground being at the bottom of our coordinate system, z equals 0, the force on the mass is just going to be pointing downwards, and it'll be of magnitude negative mg, where m is the mass of the body and g is the gravitational constant. Note that this force is a conservative force field. Specifically, the gravitational potential in this approximation becomes negative m times g times z, where z is the height above the ground level. And if you take the gradient of this function, will exactly be equal to this negative mg k hat, or negative mg in the z direction. So we'll see that this is actually a very, very fundamental aspect to this example. But let's consider the work done by this force field along two separate trajectories. In order to do this, we have to we'll define the work. We have to define what the work is for a given vector field, so a given force field, and we can do that in a very, very nice manner. I'll show how to derive that right now. So we'll do this before we get into the example. So for a constant force, call it Fc, and a constant displacement, we'll call this dc. The work done by F along the displacement dc, if we say we're moving from A here to B here, you move in a straight line, so we have a constant displacement. This vector is dc, and the force on A, we'll say, is the constant force Fc. The work done moving from A to B is exactly equal to the dot product of Fc with dc. Or if you'll remember from your basic elementary physics class, work is force times displacement, or force times distance. So this is the amount of energy done, by what I guess you could say against the force field F, or with the force field S, as you move A from B along this straight line path. And you can visualize this in a number of different ways, but perhaps the best way of visualizing this is saying that, well, we know the dot product is the length of F, or the magnitude of force, times the length of dc, cosine the angle between these two vectors, because I guess we can say that this force, I drew it along the displacement, but this constant force doesn't necessarily have to be along this displacement path. So let's make this picture here a little bit more general. obviously the force maybe looks like this, or even it could be against or with, it doesn't really matter. This force is the constant force Fc, and this is the angle between Fc and dc. So we know from our dot product that this is true, and then what this is saying is exactly, well, we know that you can interpret this in two different ways. First off, you can say that the magnitude of force I think the best way of interpreting this is saying that it's the magnitude of force cosine of theta. This is the total amount of force acting along this axis, the projection of the force vector onto this axis, and then it just multiplied by the total distance traveled. Right, so this is the force acting on this mass as it moves in this straight line path, multiplied by the total distance, or the length of this vector dc. So this is essentially why this is true about this dot product. And the idea is that we have to generalize this idea now to a general path moving in a force field that's not necessarily that's not necessarily constant. The force could be changing at every given time. So this is the simple picture, so to speak. In the more complicated scenario is now the scenario where we're moving from point A to point B along some possibly very complicated path, and for every single point on the path the force might be pointing in a different direction. And also have a different, very, very large or very, very small magnitude depending on the force field that we're moving through. So initially this seems like possibly a very complicated thing, but well, we can just define this curve as the curve C. And we know that for any curve C, we can parameterize it and get the tangent vector, t hat, the tangent vector field to the curve at every given point. And then it shouldn't take too long to see that the total amount of work done is going to be related to this idea. The work done moving from A to B is going to be exactly equal to the line integral over C from A to B of the force field, which the force in this case, this is the case of constant force and constant displacement. This is the more general case of non-constant force field F of R and also a possibly very complicated path. We'll parameterize this by R of t. So it shouldn't be hard to see here that the work done moving from A to B is going to be based on this idea, but really it's going to be the line integral of the force field dotted with the unit tangent vector, or the line integral of this force field along the curve C, because this is just F dot the unit tangent vector ds, the line integral of F dot t hat ds along the curve. the accumulation of all of these components, these dot products, give us the total net work done. I guess saying net work here should be, more specific. But this is exactly the same thing as just saying integrating with this local function at every single given point. So which is exactly what we're doing when we end up defining the line integral. Right? Because if you think about it, this right here in the constant case is the same thing as f dot d hat multiplied by the length of d. That's exactly what this magnitude of f cosine theta is. It's f dot product with d hat times the length of d. So the idea here is that we're just integrating this component at every single different point along this curve, and the total net work done moving from a to b is this line integral. This is how we define the work. We say that the work done by if it's a force field, this is going to be exactly this line integral. So back to the example, when we consider this example right here, we'll consider the work done to move a mass m in a gravitational field over two separate paths. So we'll consider the following two paths. And these will be relatively simple paths. And we'll also treat the points as relatively simple as well, just to simplify calculations as much as possible. So we'll say we'll go from the point 0, 0, 1 is our coordinate system. This will be the x-axis and the z-axis, to the point 1, 0, 0. And we'll just consider the straight line path, which is the curve z is equal to 1 minus x. And then we have the same points right here, 0, 0, 1 and 1, 0, 0. And instead of considering the straight line path for path 2, we need a different path. So we'll consider the path z is equal to 1 minus x squared, which looks like this. Now, both of these paths are paths that go from, say, a point A to a point B, the same point. And both of these paths are, we're assuming, are immersed in the same constant force field right here. But in general, right, this, depending on the example, F could be more complicated. But we're just kind of trying to illustrate something here. So we in general expect, because we have two separate paths, we expect this line integral to be different, or the line integral giving us the work to be different. So for path 1, right, we'll first start by parameterizing the curve, which you always want to do. In this case, our curve z equals 1 minus x is the same thing as, we'll choose x equals t for our parameter, and 0, and then z is going to be 1 minus t. And this is valid for t from 0 to 1. This correctly parameterizes this curve. And for our curve r of t, or a parameterization of the curve on path 2, we'll also choose t for x. So x is t, y is 0, and the z coordinate will be 1 minus t squared. And this is also valid for t from 0 to 1. And this example is nice because f is relatively simple, right? It's just the constant vector field. So f on the curve, f at r of t, is going to be equal to 0, 0, negative mg. And same thing for path 2 as well. F at r of t is equal to 0, 0, negative mg. Note that in general, f is a function of position, right? It's a vector field, so it could be much more complicated. It's just going to involve plugging in the parameterization of the curve into the function itself. That's what this f of r of t is saying. So if we continue onwards, and now that we have the vector field r of t, and we have the curve r of t parameterized, and we have f of r of t, well, we can go through and evaluate the work, or the line integral for work. I guess before we go through and do that, we know that in that line integral we're going to need the expression for r prime as well. So let's go through and calculate that first. It's always nice to stay organized and do that. This will be derivative of this with respect to the parameter, which is 1, 0, negative 1. And then r prime for this curve is going to be 1, 0. And the derivative of this function will be 2 times 1 minus t times negative 1 from the chain rule. It will be 1, 0, negative 2 times 1 minus t. So then the work is the line integral of f dot dr, which as we've seen simplifies to the line integral, in this case from 0 to 1, the normal integral from 0 to 1 of f of r of t dot product with r prime of t dt. And you remember that if you use the standard definition for the tangent vector up here in this equation right here, so the tangent vector here, the ds is the magnitude of r prime, t hat is r prime, the vector divided by the magnitude of r prime, so those cancel out, and this reduces to just this formula right here. So when we go through then and calculate the work for path 1, or the work done against the vector field f along path 1, this becomes the integral from 0 to 1 and of the dot product of this vector with this vector, which will be 1 times 0 plus 0 times 0 plus negative 1 times mg, which is just mg dt, and this is mg, the integral of 1 dt is equal to t from 1 to 0. So the work done in this case is just m times g. So this is the work done on path 1. More specifically, you can think of it as the work done against the vector field f, moving the particle in path 1, along path 1. So for path 2, yeah, that this is going to be the integral from 0 to 1, the line integral of this vector field dotted with the tangent vector. That's f of r of t dotted with r prime of t dt. And when we go through and do that, this becomes a little bit more complicated. It's going to be integral from 0 to 1, 1 times 0 plus 0 times 0 is negative 2 mg times 1 minus t. This will be 2 mg times 1 minus t dt. So this is 2 mg. Integral of 1 minus t is going to be t minus t squared over 2. from 1 to 0. This is equal to 2 m times g times 1 minus 1/2. And 1 minus 1/2 is equal to 1/2. So this is just equal to mg. We get that the total work done against f going along path 2 is also equal to mg. So this is an important example, and it really shows us a lot. It shows us that there is a certain class of vector fields for which the line integral, so that this is specifically the line integral tangent to curve C. So this third type of line integral right here is path independent. So it's not always path independent. In general, it's not. But there's a certain class of vector fields that are path independent, and it shouldn't take you long to guess what that class of vector fields are, based on where this force field is coming from. Right? For this example, the force field is coming from a conservative vector field because the force is coming from this potential function right here. And sure enough, this is exactly the condition. Right? For any conservative vector field, we're going to see that the line integral is path independent. This is a very, very important idea because this example is relatively simple, but we'll be able to show this for any conservative vector field, no matter how complicated it is. So I encourage you to do this example out again for another path. Specifically, try the path z is equal to 1 minus x cubed. Right? You'll get the exact same thing. You'll get the work along this path is still equal to mg, which is a very convincing argument for this example. So we want to try to investigate a little bit more clearly, what's going on here in this example. And it's a really important observation because this is going to essentially define when the line integral is path independent, and not only that, it's going to give us an alternative way of classifying conservative vector fields. So first, what we'll do is we'll investigate path independence. So suppose we have a vector field F, and two separate paths connecting points R and Q. The picture here looks like you have R, you have Q, you'll have some path C1, call it, and some path C2. So path independence means that for any path C1 and C2 connecting any 2 points R and Q, if the vector field is path independent, means that the line integral of f dot dr, and like I said before, for typically when we say line integral, and when you hear line integral, it means the line integral with respect to the tangent vector, the tangent field on this curve. The line integral of f dot dr over c1 is equal to c2, the line integral of f dot dr over c2. And it's very important to point out that this is the same, right, equation as the line integral over c1 of f minus the line integral over c2 of f being equal to 0, which we can rewrite using our simplifications of line integrals. This is the same thing as the line integral over c1 of f plus the line integral over c2 traversed in the opposite direction of f which is the same thing as the closed curve line integral over the union of these two paths, so the union of c1 and the union of c2 traversed in the opposite direction. So it's this closed line integral being equal to 0. Or if we call C the curve C1 union opposite direction C2, right, then path independence, which says that the line integral along any path has to be equal to one another, no matter what path you take to traverse R to Q. It's the same thing as saying the line integral along a closed curve C, composed by found by taking the union of C1 and negative C2. C is a closed curve of f is going to be equal to 0. Or the circulation over this closed curve is going to be 0. So it's actually relatively straightforward and easy to show the inverse of this statement, which is very, very nice. And the inverse of this statement is that, so this statement that we've just shown is that if the line integral of a function f is path independent, then the line integral along any two curves has to be equal, which means that the line integral over the closed curve, right, that you get by traversing the first curve, this first curve once, this is in this direction, and then traversing the second curve in the negative direction. And that's this, right, our C here is equal to C1 union C2. So that if a line integral is path independent, then for any two paths, the line integral has to be 0 over the closed curve that you get by forming the union of those two paths. We can also show the inverse of this statement very, very nicely, and that's that if the line integral is equal to 0 along any closed curve C, then the general line integral of f along C1 is equal to the line integral of f along C2 for any C1 and C2. And I recommend you go through and try and show that. It's relatively straightforward. It just involves, being able to find, for a given C1 and C2, being able to express that C1 and C2 as a closed curve, which we've already kind of talked about right here. So this is really nice, though. Essentially, we've established now everything we need to go through and show something very, very nice about vector fields, specifically about conservative vector fields. So we'll first summarize this theorem as, we've shown that if, or the line integral of f dot dr is independent of path, if and only if the line integral along any closed curve C is equal to 0. Right, so remember, if and only if is a by implication. It means we can go back and forth from either of these two statements. So the idea here, though, is that with this theorem, we have everything that we need to go through and show something really nice about what a conservative vector field must obey. And this theorem is the following. It's if f is a conservative vector field in some domain D, then the line integral of f dot dr is path independent. And we can show this by kind of breaking it up into a couple of different steps. And it's important to also note here that f in all of these fields have to be nice enough to apply the steps that we're going to apply. In this case, f must be continuous. But the idea here is that, and we'll go through the proof right here. If we assume that f is conservative on D, that means there exists a function phi such that the potential function f is equal to the gradient of phi. And so if we now consider the line integral over some path C of f dot dr, we know that if we evaluate this over the curve C, where say it's parameterized by, this is the point R, which is the position vector at A, position vector at B, it's the point Q, and then any one of these other points is R of t, and this line integral is going to be the integral from A to B of f at R of t dotted with dr, which is just R prime of t dt. And we haven't used the conservative assumption yet, so the conservative, if f is conservative, that means that this is going to be the integral from a to b of f of R of t, which is going to be the gradient of this scalar potential function evaluated right at the point R of t, because that's the vector field, and it's dot product with R prime of t dt. And this is the same thing as the integral from a to b of the gradient phi dotted with R prime of t, where the gradient of phi here is being measured at the point R of t. So I don't need to rewrite this. We can just keep this here. That's what this is saying right here. But what you should do now, right, is think of how we can simplify this. What the best way of rewriting this is going to be. And what you should do is remember how we define the directional derivative, or the if you were to take, say, the derivative, the t derivative of the function phi of R of t. So either think of the directional derivative or the chain rule. But from the chain rule, right, our chain rule applied to this composition of functions says that the derivative, the t derivative of phi of R of t, the scalar function phi on a curve R of t, is going to be exactly the gradient of phi evaluated on the curve R of t dot product with the derivative of R of t, R prime of t. So what we have inside this expression is exactly just the t derivative of the composition of phi of the scalar potential at the point R of t, and it's the integral of this derivative with respect to time, which is the same thing as the integral from phi, or the potential at A, to the potential at B of the function d phi, where phi is the, this is what happens when you make the change of variables here. So this just becomes the difference phi of B minus phi of A, and since this phi has to be a differentiable function in order for f to be a continuous vector field that's equal to the gradient of phi, that means that when if you evaluate this on a closed path, so this is just on an open path, and this alone is very interesting, because this alone is telling you that the line integral of any conservative vector field, no matter how complicated it is, if it's conservative, the line integral will always reduce on the line integral of tangent to the curve C will always reduce to just the difference of the scalar potential at the endpoints of the curve. So that's what this is telling us. Is for any conservative field, and I guess to be exact here, I put phi of B, phi of A, but we really wanted to note this as phi of R of B minus phi of R of A. which is just saying the value of the potential function at the point Q, which is the endpoint of the curve, minus the potential function at the point R. But this is really nice because it's essentially giving us this path independence. And the continuity assumption here is very important because right, if C is a closed curve, so R at A is equal to R at B, right, that means that the line integral over C of f dot dr, remember this is for the still in this theorem proof where f is a conservative vector field, this is equal to phi at Q minus phi at R. But this is a continuous function, so phi of Q minus phi of R is equal to 0 because Q and R are the same points. And this ends our proof right here. So this is really nice, and essentially what we've shown is the following two things, which I'll summarize. We've shown that if f is conservative, then the line integral of f dot dr is path independent. And we've also shown that path independence of a given line integral this is an if-then statement, so I want to emphasize here that f being conservative on some domain implies path independence, and path independence of a given line integral is the same thing as that line integral being equal to 0 along any closed curve C. Now, it's important to note here that 1 actually is a by implication, and we will see that any path independent or any vector field for which the line integral is path independent in a given domain is also going to be conservative. So you can move backwards, but for now we haven't proven this. So this is just where we're at in terms of implications and what we can use. But even this is enough to write down, say, the converse, the logical converse of 1. The converse of statement 1 would be that if the line integral of f dot dr is not path independent, then f is not conservative. This would be one way of checking to see whether the line integral along a given path is conservative or not. Alright, so if you can find, say, two paths for which the path integral is different, then the function f equal, the vector field f is definitely not going to be conservative. And I will write up here, I'll write the fact that this is in fact a by implication. So let's go through and quickly prove this statement right now. So we'll prove the theorem that if f is path independent, or if if the line integral tangent to the curve C is path independent, then f itself must be conservative. And we'll start the proof by considering a picture of our region, some region in 3D where inside this region we're saying that f is path independent. And we'll consider two paths inside this region, say one path from A to B here, and we'll consider another path from A to B prime. And alright, this is all inside some three-dimensional region omega. And this proof is going to rely on exactly this idea. So we want to first start off by making our first assumption, which is that I assume that the line integral of f dot dr is path independent. And our goal now is going to be to find, we have to find some phi such that f can be expressed as the gradient of that phi. So this is our goal for this proof. And when we go through and do this, think about how exactly we should be doing this. And the idea here is that, well, we know that due to the path independence, we're trying to write f as the gradient of some scalar field. So we want to see how does this imply that f is conservative. So that f is p of x, y, z I plus q of x, y, z j plus r of x, y, z k. And the question is how to find a suitable scalar function phi such that d phi dx is equal to the function p, d phi dy is equal to the function q, and d phi dz is equal to the function r. And the idea here is to recall what the definition of the limit is, right? And specifically we recall that, say, well, I'm just going to do this for the x partial derivative. So for the first component, the x component The idea, though, is that this argument applies in general regardless of the component. We can always make this almost exact same argument for either component. So let's say that b and b prime look like this. They're along the x-axis. And recall that actually if we denote the point B as the point x, y, z, and B prime as the point x plus h, y, z for some value of h, right, we have that the partial derivative of phi with respect to x is exactly, by the definition of partial derivative, the limit as h goes to 0 of phi of x plus h comma y comma z minus phi of x comma y comma z divided by h or equivalently the limit as h goes to 0 of phi of b, the scalar function at b, minus the scalar function at b prime divided by h. So remember, this is the definition of the partial derivative of any scalar function. And the idea here is that we're looking for the way forward for defining, right, this phi function. So without loss of generality, let's go through and do this. We'll define this phi function. We'll define the function phi of the point B, or the function phi at the point B, to be exactly the line integral from a to b of f dot dr. And we can make this definition exactly. And if we define this function phi of b to be the line integral, there's no problem with doing that. Right, we then have the definition of the partial derivative, right, d phi dx, which gives us the following. And we don't even have, before we even use this partial derivative limit, we have that if you just consider phi at b minus phi at b prime, this is the same thing as the integral from a to b of f dot dr minus the integral from a to b prime of f dot dr, which from our simplifications for line integrals is just the line integral from the point B to the point B prime, or from the point B prime to the point B. This is the same thing as the line integral from B prime to the point B. And the key thing here is to exactly now consider this definition of the partial derivative. We're going to use the actual exact definition of the partial derivative because with this definition for this potential function, if we say that for some point B and some point A, we define the potential function as being equal to the line integral of the vector field from A to B. Then for any other point B prime, phi of B minus phi of B prime is just going to be the line integral from B prime to B. And now remember, we've assumed path independence, so the path going from B prime to B doesn't matter taken when evaluating this integral. Right? Any path from B prime to B will be the same value of this line integral because of path independence. So what we'll do is we'll consider the simplest possible path from B to B prime, which is exactly a straight line. So we'll consider the straight line path along the x-axis from B to B prime, where we'll call this distance right here h. Or this distance is going to be not h, but it's just the distance of this straight line, which we can definitely parameterize, so that this distance right here is equal to h. So let's put h right here. And so then what we have is the following expression. We have that first off, well, from the partial derivative, the expression for the partial derivative, d phi dx is equal to this limit right here, which is the same as the limit as h goes to 0 of the integral from b prime to b of f dot dr divided by h. And if you recall, you'll remember that this is the same thing, right? We're using the definition of the line integral as saying that d phi dx is equal to the limit as h goes to 0 of, we'll parameterize our curve with the parameters t going from 0 to 1 of f of r of t dot product with r prime of t dt all divided by h, where r of t is the curve, or specifically the straight line from b prime to b, which is exactly equal to the line that at t equals 0 starts at b prime and passes through the point b. So it's equal to at the point x, y, z plus h times 1 minus t 0, 0. And this is for t from 0 to 1. And this works because this is exactly giving us all of the points on this line right here from b to b prime. Not only that, but we can calculate the tangent vector to this line, r prime, relatively easily, taking the derivative here, which gives us negative h times 1, 0, 0, or negative h times I hat. And if we plug in to this equation, then this becomes the integral of f of r. Remember, f of r of t is the same thing as PQR, all evaluated at r of t. And this is the dot product then with r prime, which is negative h times I dt. Well, the h is constant in this integration with respect to t, so it comes out and cancels with this h. And what we're left then is d phi dx is equal to the limit as h goes to 0, integral from 0 to 1 of the dot product of this with I hat is going to be P, a negative sign on the outside here. Okay, this is going to be just P of x of t plus h times t, or not x of t, just x plus h times t. Because that's the x coordinate of the point B. And then y z dt. And this is where we want to use one of our theorems from Calculus 1. This entire thing is just a nice function of t, and we can use the mean value theorem from Calculus 1 to assert that there's going to be, and this is because this is a continuous function. P is a continuous function of all of its arguments. So at any point x, y, z, it's a continuous function of the x argument, and therefore this composition is continuous. And by the mean value theorem, there exists some value t star such that the following is true. d phi dx is going to be equal to the limit as h goes to 0 of this function evaluated at t star multiplied by the size of the domain. And so d phi dx is equal to the limit as h goes to 0 is -1 of p of x plus h times t star y z. And the last thing to note here is that t star is between 0 and 1, so as h goes to 0, t star is constant. This is a continuous function, and therefore this is going to be the same thing as being equal to negative p of x, y, z. And the conclusion here is that we can do the exact same thing for the y-axis and the z-axis as well. So using the exact same method and the exact same idea, we can go through and show that d phi dy is equal to negative q of x, y, z at every point in this domain, and that d phi dz is equal to negative r of x, y, z. And so therefore the vector field f that we started with will in fact be equal to the gradient of phi, and you have a negative sign here, but you can just recall this. This is the same thing as saying that it's equal to the gradient of psi, where psi is negative times phi. So the point here is that we've shown that this is in fact a conservative vector field, and we've proven the theorem. But the idea here is that the main use of this statement is that if the line integral is not path independent, then f is not conservative, and we can actually use this very, very nicely. We can use this directly to find a counterexample to the one of the theorems that we talked about before. So let's take a look at the vector field given by 2D y over x squared plus y squared times -1 plus, and the y component is going to be x over x squared plus y squared. So one of our main things to look at here is to look at the curl of the vector field f, and sure enough, if you take the curl of this vector field, you're going to get that it's equal to 0. Right? It's always important to look at the curl and the divergence of a given vector field, But so you want to check this. Go through and check this calculation right here. I'm not going to do it, but it is similar to some of the homework problems. And you'll remember that we had that previous theorem that was proven that said that. So recall, if a vector field F is conservative, then the curl of F is equal to 0. And I told you to be very, very careful about using this theorem. It's only a one-way theorem. You can't go backwards unless some suitable restriction is made to this statement. And this is a great example of a field for which we have to be very, very careful, because the curl of this field is equal to 0. However, if we go through and look at the line integral, right? And if I am very, very careful here, this is we'll see here. I can give you a hint of why things are not going to work out so nicely for this field. Right, this field is it's not defined at the origin. If you take the limit of either of these two component functions as x goes to 0, 0, you'll see very clearly that we have to remove 0, 0 from the domain of this function. So what this looks like, if we kind of plot this out, is that we have some hole at the origin. That being said, we can still visualize this vector field very, very nicely, and we can do that in Python just by taking a look at the Python window. And running our visualization. So like this is what this vector field looks like, and you can definitely see that it is, sort of, it looks like it's rotating around the origin, this origin point right here. So initially you would expect that the rotation of this vector field is non-zero, but we just showed the curl of this vector field, and that's what you should go through and do. Take the derivatives and show that the curl of this vector field is equal to 0. So technically, it's irrotational at any given localized point, and this is a little bit confusing, and it looks a little bit confusing. And the way out here is to kind of take this idea and let's consider two separate paths. And we'll consider a path that surrounds the origin and a path that is away from the origin. And you can do this with any path, but we'll just use a circle. So we'll have two separate circles. This is our path 1 that surrounds the origin, and this is our path 2 that is separated from the origin or away from the origin. And what we'll also consider is that the tangent vectors to the curve, to each one of these curves, combined with the vector field at those points on the boundary of this curve. So if we do a plot of that, this is what we see right here. Each one of these curves, where in red here is the tangent vector to the curve, and in blue is the actual vector field at each one of these individual points. And you see that for like this curve right here, the vector field is pointing in all sorts of different directions depending on how the curve is rotating, compared to the tangent vector, because this path is moved away from the origin, and this path is centered around the origin right here. And let's consider this at a whole bunch of very small points. The magnitude of this projection, the dot product of the vector field at each point on the curve, and the tangent vector at each point on the curve, and make a plot at each point of what this value is. That's what this looks like right here. I'll make it even bigger so we can kind of see this right here. It's a little bit out of scale when I do that, but you can still see what we're talking about. So this projection, right, and this is the color bar, so each one of these colored points on each one of these curves represents the value of the dot product of the vector field and the tangent vector at each one of those points. And you see that this curve right here that's going around, right, the origin has a relatively constant value here around 0.9, right, which is the constant value of the dot product of the vector field with the tangent vector, right, which is definitely due to the fact that this vector field is circularly symmetric, or symmetric around this point. But alternatively, if you look at this plot right here, you see that the maximum value for this dot product is around a little bit over 0.25, or this high yellow value right here, and then gradually, right, as you rotate around the vector field, well, this right here, you're starting at around 90 degrees, so you're around 0 for the actual projection, and as you move around, you get to a maximum value of around 0.25, which corresponds to the vector field pointing essentially, it's pointing along the curve in the direction of the tangent vector, and then as you move in this direction more and more, you get closer to 0 because the vector field is getting closer and closer to tangent, or perpendicular to the tangent to the curve, until the point where you're here and the vector field is pointing in a different direction than the tangent to the curve. This is why it gets all the way down to around negative 0.75 right here. And this, I think, is a very, very nice picture because it clearly shows that even in this small portion right here on the curve, the maximum projection gets, or the minimum projection gets to a value of negative 0.75 on this curve, in this about a quarter of the curve right here. And then for about 3/4 of the curve, right, the maximum projection gets to around 0.25 right here. And this is actually hinting at something extremely kind of neat, right? If you go through and do the line integral around any path, actually, you'll be able to show that when you move away from the origin, the line integral around this vector field around any path is going to be 0, right? So, if we consider like just a domain out here, where any path inside that domain that's away from the origin, the line integral will be 0. And therefore this function will be conservative on any region that does not contain the origin. However, right, the line integral around this path right here is clearly going to be non-zero. It's not going to be equal to 0. So the origin is our problem point for this this expression, for this example, and we're seeing now that this picture is clear enough evidence that this vector field is not conservative, and we'll see that exactly in the following. So if we go ahead and open up this plot again, we know that we have our vector field here that's rotating around the origin, and we'll consider the line integral just around a path, say, that contains the origin, and we'll stick with a simplified path of radius epsilon, so a circle of radius epsilon. The integral, the line integral on this path is going to be line integral on C, or from, we'll say C from the circle, it's from 0 to 2 pi of f of r of theta dot product with r prime of theta d theta, where r of theta is epsilon cosine theta epsilon sine theta. If you want to think of this as in 3D with 0 here because this is just a two-dimensional vector field, r prime of theta is going to be negative epsilon sine theta epsilon cosine theta. And when you plug in to find f of r of theta, it's plugging r of theta into the vector field f. This is equal to negative epsilon sine theta, and x squared plus y squared will just be epsilon squared. You'll have epsilon sine theta, it'll be positive epsilon cosine theta, that's this x, the x coordinate, over epsilon squared, and then 0 is the third component. I guess really we don't have to consider the third component until we consider the curl of the vector field. That's just making things a little bit too messy. So f of r of theta is just going to be negative sine of theta over epsilon cosine of theta over epsilon. So when we go to evaluate this line integral, this becomes the integral from 0 to 2 pi of this vector negative sine theta over epsilon cosine theta over epsilon dot product with r prime, which is negative epsilon sine theta cosine theta. And going through and doing this integral, well, when we do the dot product, we multiply these two things together, we get sine squared. We multiply these two things together, we get cosine squared, so the resulting epsilon over epsilon is 1. So we're just going to get this thing is right here is sine squared theta plus cosine squared theta, which is equal to 1. So this is the integral from 0 to 2 pi of 1 d theta, which is 2 pi. Right, so this value, the value of the circulation around this circle, is in fact just equal to 2 pi. That's the circulation of this vector field around the circle of radius 1. And now this is it. This shows us that this vector field f cannot be conservative on the indicated domain, because we found a closed path, and I held off from writing this and mentioning this because I wanted you to think about it, but this path C is a closed path. Right? It's the circle of radius epsilon, which is a closed path. This is a closed path that's giving us a non-zero line integral, right? And what that means, going back to our theorem, is that this is not path independent, because we have that the line integral along any closed curve C should be equal to 0. Oh, and I forgot to write this equal to 0 along any closed curve C implies path independence. what this means is that because we found a path for which it's non-zero, then this integral is not path independent, and therefore, because it's not path independent, the function is not conservative. So there exists no scalar potential function phi to express this vector field as the gradient of that scalar potential function. And what we're going to do is we're gonna investigate and see, right, why this by implication actually does hold, right? And we're going to kind of investigate exactly what it is that's failing here. And you probably, if you're thinking about the origin, you're right, right? The idea here is that this vector field in this domain that we're looking at is what's called a multiply. It's not a simply connected domain. It's what's called multiply connected, right? There's a hole or a missing point in this domain. This is actually a very, very deep result topologically, and goes to a very deep area of differential geometry known as Theorem cohomology. So we won't be talking about much of that here, but it is very, very important to point out. And the idea here is that we're seeing that this, you have to be very, very careful with statements like this, because this is saying if f is conservative and the curl of f is equal to 0, you can't go backwards. We'll see that you can go backwards on a simply connected domain, right? So if we add to this statement that if f is conservative on a simply connected domain, it's going to turn out that this becomes an if and only if statement. But this example very clearly shows that it's not an if and only if statement unless we include certain restrictions on the domain. So let's write down the statement of this theorem, which we won't be able to prove yet, but we'll prove it once we end up showing what's called Stoke's theorem. So we're going to say let omega be a simply connected domain in three-dimensional space, and we also have that an analog of this theorem holds, right, in 2D as well. We'll see that as a special case. And we have the statement that f is conservative in omega in 3D or D in 2D if and only if the curl of f is equal to 0 at every point in omega, or f is irrotational. In omega. So this is a big theorem, and it's saying it's very, very important that we've seen from the previous example that this region be simply connected, a simply connected region. But if this is the case, then we do have the by implication of this statement right here, our previous theorem on conservative vector fields, which is really nice and very, very useful. But we can't prove this yet. The proof is going to come from what's called Stoke's theorem. But right, if we move back to our previous example, we see that this is very, very nice. So like the previous example on gravity, we had that the force vector was negative mg k hat, and we know that this vector, you can say that, well, if you just take the curl of f, this vector is defined everywhere on all R3, and the curl of this vector field is definitely equal to 0, right? Because this is a constant vector field, so therefore, because the domain of the vector field is simply connected, right, by that theorem, then f is conservative. So it's important to emphasize here that simply connected means with no holes in the domain, or another equivalently, you can think of it as any closed loop can be shrunk down to a point inside the domain. It's another nice way of thinking of it. But the idea here is that this theorem only works if the domain is simply connected. But for the previous theorem, or the previous example, right, it doesn't work because there's one hole in this domain, and just because the curl of this vector field is 0 doesn't mean that it's a conservative vector field, and we definitely showed that because we found a path for which the line integral was non-zero, a closed path for which the line integral was non-zero. So the last thing that we want to look at here is that, well, if we have a given vector field and we somehow, we know that it's conservative, or we suspect that it's conservative, how could we recover the potential function? So given a vector field f that is curl free, on a simply connected domain, how can we recover the scalar potential? So for example, we'll start with the following vector field. F is equal to cosine of y 1 minus x times sine of y, and we'll say that the z coordinate is equal to 1. Alright, so if this is conservative, it certainly has it's continuous everywhere. Each one of these functions is continuous. Right? It's defined on all of R3, so there's no holes, and the domain is simply connected. So this is continuous, and it's actually infinitely many times continuous. You can take the derivatives of this vector field infinitely many times, but the main thing is that it's continuous on a simply connected domain. And if you go through and evaluate the curl of this vector field, curl of this vector field is going to be, this is P, Q, and R. Curl is going to be the y partial derivative of R minus the z partial derivative of Q. It's going to be the x partial derivative and negative times the x partial derivative of R minus the z partial derivative of P, and the x partial derivative of Q minus the y partial derivative of P. So dr dy is d1 dy, which is 0. And then dq dz is going to be the partial derivative of this function with respect to z, which is also 0. dr dx is going to be 0. dp dz is going to be the derivative of cosine of y, partial derivative with respect to z, which is 0. And then dq dx is going to be negative sine of y, and then minus the y partial derivative of p. Y partial derivative of cosine of y is negative sine of y. So this becomes sine of y minus sine of y, which is also 0. So this is exactly equal to the 0 vector, because this function is defined and it's continuous on a simply connected domain. That means that this function is conservative. And remember, we have not proved that yet, but we will get there in subsequent lectures. We get to Stoke's theorem. And the idea then, and what's really nice about this is that, so we know this is going to be equal to the gradient of some phi. So this vector field PQR will be equal to, right, P is the x partial derivative of phi. Q is going to be the y partial derivative of phi. And R is going to be the z partial derivative of phi. The question is how to solve for this phi. So we'll go through and integrate one of these equations to try and see what happens here. So what we're going to do here is we just consider the integral. So we know that the indefinite integral of the partial derivative of phi with respect to x, we integrate this with respect to x, this is the same thing as the integral of the function p with respect to x. And we know that this is going to be equal to, in general, phi itself. And this becomes the integral of p dx plus, in general, it's not going to be a constant. It's going to be a function of x and y, or a function of y and z. So in general, right, when we integrate both sides of this expression right here, we have to include not a constant, right, because we're only integrating a partial derivative. But if we go through and check this, right, we'll see that this works out really nicely. Because if you take the partial derivatives of both sides of this expression, what you're going to end up getting is the partial derivatives. This is just kind of a check over here. I'll do it over on the right to show that this is making sense. When you take both the partial derivatives of both sides of this expression with respect to x, you get the partial derivative of the indefinite integral of p dx, which is just going to be equal to p itself, plus the partial derivative of a function of y and z, which is going to be equal to 0. Right, so this is giving us exactly this the first component. And this is important because it's kind of like, it's exactly what you would expect from a single variable calculus course, but you have to be very careful here. This f of yz is in general a function of y and z that's unknown, but we have to solve for. So specifically, this is telling us then that phi is equal to the integral of p, and p is the function cosine of y. Dx plus some function of y and z. So phi is equal to, well, the antiderivative of cosine of y with respect to x is just x times cosine of y. So this is really the first step now that we've verified what we need to know about getting this first step in satisfying, right, the first component of this equality right here. So we still don't know what f is. We have to go through and solve for f. And we'll do that by using our second condition, which is that the y partial derivative of phi has to be equal to 1 minus x times sine of y. And if this is our equation for phi, which it has to be if the first equation is satisfied, right, we have to take the y partial derivative of this, and this is going to say that, well, the y partial derivative of x times cosine of y is negative x times sine of y plus the y partial derivative of f, whatever that is. And this gives us a very nice equation. It gives us the equation that the partial derivative of f with respect to y is equal to 1 if we add x times sine y to both sides of this expression. So we can do the same exact thing here to get, we can take the antiderivative of both sides of this expression, right, to get that f itself has to be equal to y plus some general function g of z. Right? Because if you take the antiderivative of both sides of this expression with respect to y, you get the antiderivative of the partial derivative of f with respect to y dy. So if we take the antiderivative of the left-hand side here, you get the antiderivative of 1 is going to be y plus some function g of z, general function that we don't know yet, we have to solve for. And the antiderivative of this with respect to y is just going to be f. This function g of z is determined, right, by the third condition. You can check this, right? If you take the partial derivative of this expression with respect to y, on the left-hand side you get df dy, on the right-hand side you get 1 plus the y partial derivative of g of z, which is 0. So it's recovering this right here. But this expression for f inside this expression for phi will give us another simplification. We have that it's equal to x cosine of y plus f, which is y plus g of z. And we're almost done here, because this expression for phi will satisfy the first two equations in our system here for the conservative vector field f. So the last equation that we have to make sure is satisfied is that the z partial derivative of r is, or the z partial derivative of phi is equal to r. So d phi dz, is equal to r, which is 1. And with f being equal to this, d phi dz is going to be, well, the z partial derivative of this is 0. The z partial derivative of y is 0. So we're just left with g prime of z. The z partial derivative of g of z is g prime. And if we take the integral of both sides of this equation with respect to z, or the antiderivative, this is equal to 1, and so we have that phi we'll just use the first and second here, so that the integral of g prime of z, antiderivative of g prime of z is just going to be g of z. And this is going to be equal to the z integral of 1, which is going to be 1, or it's going to be z times plus some constant. This is just from calculus 1. So we have g of z, and therefore our function, our potential function, which is a function of x, y, and z, or just a function of position r, is going to be exactly equal to x times cosine of y plus y plus g of z, which is z plus a constant. And this right here is exactly the correct expression for phi. So we've solved for our scalar potential function, and it's always going to be determined up to an additional constant because of integration. It's the same thing as for single variable functions. A good problem for you to look into is sort of a change in this problem just a little bit, right? What happens if we spoil this problem? So let's change the system a little bit. We'll say, what if we investigate the vector field f equal to cosine of y plus z 1 minus x sine of y and 1 cell. So first things first, if you take the curl of this vector field, you'll see that it's not curl free. It's not equal to 0, the curl. Therefore it's not conservative. But nevertheless, you can try and proceed similar to how we proceed here, right, and going through and solving for that potential function. And this exercise is a good exercise because what you're going to want to do is try to find a contradiction. So try to find why f itself cannot be equal to the gradient of phi for any scalar potential for this example. But this will end the lecture for today. This is a very, very important topic, and what we'll be moving into in the next lecture is going to be the definition of what's called a surface integral. So thank you very much for listening to lecture today, and I hope you have a great day.